What's up, guys? We're working on homework 2, number 5 here. It's this problem from the homework. Basically, we have the disc sitting on top of the platform attached to 2 springs, which are then further attached to 2 fixed walls. And what we want to do is find the equation of motion for each of the 2 masses. Okay, so we'll come over here and to get started with the analysis, we'll do the free body diagram of each of the different pieces. Right here we have the first spring, and there's an F1 connecting that to the M1 over here, equal and opposite forces. And then M1 and M2, which is the disc, are in contact. So we have a force that we call it F of C. And this F of C is in the clockwise orientation to match with the angular displacement of the disc. And then this one is just equal and opposite on the force on the mass M1 by Newton's law. And then right here we have a force dependent on time, which we have F of T, and that's just in the problem. We don't have any values for it or anything like that. And then we come up here, and the only other force left is the spring force that we named F2, and that just attaches the disc to the spring, and those are equal and opposite as well. So we'll get started on writing the equations for each of the different pieces. So right here, we have this one spring. It's attached to a fixed wall. So the relation we're going to get for this one is F1 equals K x1. Okay, that's pretty easy. It's just positive because F1 and x1 are in the same direction. That's how we've been doing it. Coming over here, it's a little bit different. We have a slightly different relation. This one's just going to be F2 equals negative K x2. And that's due to the fact that F2 is in the opposite direction from the displacement, the coordinate system that we set up at the beginning of the problem. Oh, and by the way, I didn't mention the coordinate systems before, but this is x1 right here, x1 or x2, and then this is x1 for the block, and then x2 over here, and we'll use those in the rest of the problem. So next thing we have to do is look at the angular motion of this, and we'll write an equation for the disc, and that's going to be I for the disc times theta double dot, which is just the angular acceleration alpha, equals FCR. And that's FCR is positive because FC is pointing in the clockwise direction, and that'll cause it to move in the motion that we have specified, so everything's positive. The only thing is, in the equations of motion, we don't want theta double dot, we want x2 double dot and x1 double dot for our equations. And so we have to find a relation between the angular motion of the disc and the displacement that's going to cause. So that's given by this equation right over here, which is R times the velocity, angular velocity, equals x2 dot minus x1 dot. And this goes with what he said in recitation. Basically, the amount that this is spinning is how far it's going in the x2 direction minus how far it's going on the bottom here in the x1 direction. So if it's going positive, x2 will be bigger than x1, and so on. So to get x2 double dot and x1 double dot, we have to take the time-dependent derivative of each of those. R doesn't, that's a constant. Time doesn't affect it, but we'll just get R theta double dot equals x2 double dot minus x1 double dot, and rearrange this to find a substitution for this theta. So we'll just get theta double dot equals x2 minus x1, both of those are double dot, over R. So coming back over here, I'll probably write it in this space right here. We want to solve for FC, and plugging that expression in for this right here, we have FC equals I x2 minus x1 double dot for both those over r squared. And then substituting in the I for the disk equals 1/2 mr squared. We'll plug that in right here. FC equals, well, you plug it in, and then there's a bit of cancellation. But what you're going to find is that FC equals 1/2 m x2 double dot minus x1 double dot. And so that's good. So the next thing we'll do for this problem is find the equations of motion, which is basically our end goal. So we definitely want to do that next. Let's start off with M1. The equation of motion for M1 is going to be this. Mx1 double dot, the acceleration, equals f of c in the positive x direction as specified by x2 minus f1 plus f of t. And you can see that right from the free body diagram, negative f1, positive ft, and that should be good. Now, the next thing we have to do is the equation of motion for the disk M2, which is this. Mx2 double dot equals negative fc plus f2. And basically what that is the disk. You have negative fc going in the negative x direction, positive f2 going in the positive x direction. So all you have to do after that is sub everything back into those equations right there, and we'll get our answer. So this first one, we're going to call this 1. This one's 2. Let's make sure I didn't miss anything. Yeah, we should be good. We're gonna be using this. We're gonna be using this expression and this one over here to plug back into those equations, and that should give us our answer. So after plugging everything in, this is what you get. The first equation is going to simplify to this form that I'm about to write right here. Number 1 is going to be 3/2 m x1 double dot minus 1/2 m x2 double dot plus k x1, and that is going to equal the forcing, which is f of t. Only include that f of t on the right side of the equation. Equation number 2 is going to simplify to this right here. Negative 1/2 m x1 double dot plus 3/2 m x2 double dot plus kx squared, or kx2, I'm sorry, equals 0. And so this will be our 2 equations for this system. You gotta have the 2 equations for the 2 masses and the 1 equation that describes the relation between them. But good luck on the quiz, everybody, and thanks for watching.